Last time we learned that Euler integration allows one to approximately solve an ordinary differential equation. What do we do if we have an ordinary differential equation that we want to solve exactly? For general f of x and x dot equals f of x, we cannot expect an exact solution, but for linear, constant coefficient, first-order ODEs, we can. Having a good guess matters a lot, and for us, that guess will always be the exponential solution. X of t is equal to e to the ht times some constant. And in this case, it'll be x naught, the state x at time 0. And h is an unknown parameter. This says that we expect a solution to an ordinary differential equation to be an exponential times the initial condition x of 0, which is x of t at time t equals 0, which we assume to be the initial time. Notice that if h is greater than 0, this solution will blow up and go to infinity if x of 0 is non-zero. If h is less than 0, then it will go to 0. This observation is a good way to have some physical intuition about what the exponential function means and if it makes any sense. What does it mean to solve a differential equation anyhow? We didn't really get into this question in the last lecture, but it is helpful to think of x dot as the time derivative. That is, x of t is equal to f of x of t is the same thing as saying that d dt of x of t is equal to f of x of t. So you see that what you're really saying is that x solves the differential equation if plugging it into the left-hand side, that is taking its time derivative, is the same as plugging it into the right-hand side, that is evaluating f at x of t for all time. To see how this works, let's assume that our spring damper system, which again has a wall, a spring, and a damper, and an external force that we assume is going to be 0. We assume that this has an exponential solution and plug into the differential equation to find the value of h. So we have x dot is equal to minus k over b x. We are assuming that d dt of x of t is equal to minus k over b x of t. And if we plug in the exponential solution, we get d dt of e to the ht is equal to minus k over b e to the ht. And don't forget that there's an x naught multiplying both of those. Now, if we take d dt of this exponential, the only thing that comes down is we have h coming down from the exponential is equal to minus k over b e to the ht x sub 0. Now, first note that if x sub 0 is non-zero, we can divide by both sides and get rid of it. And e to the ht is always non-zero, which means that this tells us that h is equal to minus k over b. And that means that our solution is e to the minus k over b times t all times x naught. If we now specify that k equals 1, b equals 1, and x equals 0.5, then we see that x of t is equal to e to the minus t times 0.5. Note that this behavior is somewhat unintuitive. It says that if I extend the spring damper system by 0.5 units, then I will see it move forever, which of course a real system won't do. This is largely because damping tends to be nonlinear at very low velocity, suggesting we can never fully believe our analytical models or computational models. But this solution will capture the behavior of many spring damper systems. Moreover, we can now compare the results of the analytic solution to the results of Euler integration. Note that the large dt is not very close to the analytical solution, but the small dt is. This means that you have to use your judgment when choosing the dt for your simulation. Today we learned about exponential solutions to ordinary differential equations. Exponential solutions are valid for any linear, constant coefficient, first-order differential equation where the external force is 0. And we will be talking about them occasionally for the rest of class. For now, keep in mind that an analytic solution exists for many engineered systems that you will encounter, and certainly all of the ones we will see during the rest of this class.